So let me tell you about bridges. Not in a way that feels like a textbook, not with diagrams and equations, but the way you'd hear about them if you and I were sitting on a porch somewhere late at night, maybe watching the lights of a distant highway overpass blinking in the dark, and I just started talking because I couldn't help myself. Because bridges, honestly, are one of those things that get more interesting the longer you think about them. And tonight, we've got all the time in the world. Here's the thing about a bridge. Every single day, you probably cross one without even noticing. Maybe it's a little concrete overpass on your commute, or a pedestrian walkway over a creek, or some massive suspension bridge that takes your breath away when the fog clears. And in that moment, you're trusting it. You're trusting that somebody, probably a long time ago, figured out exactly how to make this thing hold you up. You don't think about it. Nobody does. But somebody had to think about it and the story of how humans learned to think about it. That's what I want to tell you tonight. Let's start at the very beginning. And I mean the very beginning, before anyone had a word for engineering, before mathematics, before writing. Imagine you're a person living maybe 10,000 years ago, maybe longer, and you need to get across a river. The river isn't that wide, but the water's fast and cold, and you've watched it carry away branches and small animals after a storm. You need to cross. What do? Well, the simplest thing in the world. You find a fallen tree, a log that's come down in a storm and happened to land across the water, one end on your bank, the other on the far side. And you walk across it. That's a bridge. That is, in the most fundamental engineering sense, a beam bridge, a horizontal thing, supported at both ends, carrying a load, you, across a gap. And everything that comes after, every cable-stayed marvel and every soaring arch, every bridge that's ever been built in the history of the world is just a more sophisticated answer to the same question that Fallen Log answered. How do I get from here to there when something's in the way? Now, think about what's actually happening when you walk across that log. Your weight pushes down on it. Gravity is pulling you toward the center of the earth, and the log is the only thing between you and the water. The log doesn't fall because its two ends are resting on solid ground, the banks of the river. Those contact points, where the log meets the ground, engineers call those the supports, or the abutments. The space between them is the span, and the log itself is the beam. Here's what's beautiful about this. When you stand in the middle of that log, your weight creates forces inside the wood. The top of the log gets compressed, squeezed together, because it's being pushed inward. The bottom of the log gets stretched, pulled apart, because it's being bent downward. Compression on top, tension on the bottom. That's bending. That's what a beam does when you load it. And if the log is strong enough to handle both of those forces without snapping, you make it across. If it's not, well, you get wet. Or worse. This compression and tension thing, by the way, is going to come up again and again tonight. It's the fundamental language of how bridges work. Every bridge ever built is just a clever arrangement of parts that are either being squeezed or stretched. That's it. Two forces, compression and tension. The whole art of bridge engineering is figuring out how to manage those two forces, how to send them where you want them to go, how to make sure no single part of the structure is being squeezed or stretched beyond what it can handle. Keep that in the back of your mind as we go. So our ancient ancestors figured out the fallen log, but pretty quickly, you can imagine, they wanted more. The log only works if the river is narrow enough for a tree to span it. What if the river is wider? What if there's no convenient tree? What do you do then? One answer, and this is genuinely ancient, we're talking thousands and thousands of years, is the Clapper Bridge. You might have seen pictures of these if you've ever looked at old stone structures in places like Dartmoor in England, or parts of ancient Greece or China. A clapper bridge is about as simple as a bridge gets. You take flat slabs of stone and lay them across stone piers, basically stacks of rocks set into the riverbed. The slabs span from pier to pier, and you walk across the top. It's the same principle as the log, the same beam concept, but now you're using stone instead of wood, and you're breaking the crossing into shorter sections with those intermediate supports. And this is a really important idea, so let's sit with it for a second. By adding supports in the middle of the river, you've made each individual beam shorter. And a shorter beam is much, much stronger than a longer one. Think about it this way. If you hold a ruler between your two hands and press down in the middle, it bends easily. But if you move your hands closer together, shortening the span, it's much harder to bend. Same ruler, same material, but the shorter span makes it dramatically stiffer and stronger. That's why clapper bridges work. Each stone slab only has to span a short distance between piers, so even relatively thin slabs of stone can carry the weight of people and animals crossing over. The problem with stone, though, is that it's terrible in tension. Stone is fantastically strong in compression. You can stack enormous weights on top of it, and it just sits there, perfectly happy. But try to stretch it, try to pull it apart, and it cracks. It's brittle. And remember what we said about beams. The bottom of a beam is in tension, so a stone beam can only span a short distance before the tension on its underside causes it to crack and fail. This is why you never see long, flat stone beams in ancient architecture. The spans are always short because stone can't handle the bending. Now, some incredibly clever person, or more likely a long series of clever people over centuries, figured out a way around this problem. And it's one of the most beautiful ideas in all of engineering. The arch. Here's what's so brilliant about an arch. Instead of laying a flat beam across a gap, you arrange stones in a curve. Each stone is wedge-shaped, wider at the top than at the bottom, and they all lean against each other, pressing inward. The stone at the very top of the arch, the one right in the center, is called the keystone, and when it's dropped into place, it locks the whole thing together. Now, when weight pushes down on top of the arch, that downward force gets redirected. Instead of creating bending, with compression on top and tension on the bottom like a beam, the arch converts almost everything into compression. The force flows down through the curve of the stones, each one pressing against its neighbor, all the way down to the supports at the base. And this is the magic. Because stone is so good at handling compression, an arch made of stone can span much, much farther than a flat stone beam ever could. You've essentially eliminated the tension problem by changing the shape. You've taken a material that's weak in one way and arranged it so that it never has to face that weakness. That's engineering. That's the essence of it. Not fighting nature, but working with it, finding the geometry that lets your materials do what they're naturally good at. The ancient Romans didn't invent the arch. It shows up in Mesopotamia and Egypt and other places long before Rome, but the Romans perfected it. They took the stone arch and turned it into something almost industrial. They built arched bridges all across their empire, from Spain to Syria, and some of them are still standing today. Think about that, 2,000 years, and they're still there. The Pont de Gare in southern France, built around 19 BC to carry an aqueduct across the Garden River, stands about 160 feet tall, with 3 tiers of arches stacked on top of each other. It carried water for centuries, and today you can still walk across it. The Alcantara Bridge in Spain, completed around 104 AD over the Tagus River, has a main arch spanning about 98 feet, and it still carries traffic. 2 millennia of floods and wars and earthquakes, and it's still doing its job. What made the Romans so good at this wasn't just the arch itself, it was their understanding of materials. They developed a form of concrete, a mixture of volcanic ash called pozzolana with lime and water, that was remarkably strong and durable. They could use this concrete to fill in the cores of their structures, using cut stone on the outside as a facing, but relying on the concrete for bulk and strength. This let them build faster and bigger than anyone before them. Their bridges weren't just functional. They were statements. They said, "Rome is here, and Rome builds things that last." But let's talk about what's actually happening inside one of those Roman arches, because it's really satisfying once you see it. Imagine you're standing on top of the Alcantara Bridge, right at the middle of the main arch. Your weight pushes down. That force enters the stone of the arch and gets split. Some of it goes left along the curve, some of it goes right. As it travels along the curve, it's all compression, stone pressing against stone. When the force reaches the bottom of the arch, where it meets the massive stone abutments on each bank, it pushes outward and downward into the ground. The abutments have to be enormous and heavy because they need to resist that outward push. If the abutments aren't strong enough, the arch spreads apart at the base and collapses. This outward force at the base of an arch is called thrust, and managing it is one of the central challenges of arch bridge design. The Romans handled it by making their abutments absolutely massive, huge blocks of stone sunk deep into the riverbanks. Overkill by modern standards, maybe, but it worked. And when they built multi-arch bridges with several arches in a row, the thrust from one arch would push against the next arch, and they'd balance each other out. The only arches that needed really heavy abutments were the ones at the ends. It's like a row of people leaning against each other. Everyone in the middle is held up by their neighbors, but the people on the ends need something solid to lean on. Now, I want you to notice something. We've gone from a fallen log to a stone arch, and the fundamental question hasn't changed at all. How do we get a load from one side to the other? The log does it by bending. The arch does it by compressing. Different mechanism, same goal. And the reason the arch works better for stone is that it plays to stone's strength. A wooden log can handle some tension, so a beam works okay for short spans. Stone can't handle tension, so you need the arch to keep everything in compression. The material dictates the form. That's a principle that's going to echo through everything we talk about tonight. After Rome fell, bridge building in Europe slowed down dramatically. The knowledge didn't vanish entirely. Monks and local builders kept constructing small stone bridges throughout the medieval period. But the scale and ambition of Roman engineering wouldn't really be matched for nearly 1,000 years. Medieval bridges were often narrower, rougher, and built with less precise stonework. Many of them had houses and shops built right on top of them, which seems wild to us now but made perfect sense at the time. A bridge was a choke point where everyone had to pass, so it was prime real estate. Old London Bridge, the famous medieval one that was started in 1176 and took over 30 years to build, had so many buildings on it that it barely looked like a bridge at all. It looked like a street that happened to be over water. It had 19 narrow arches, and the piers were so thick and closely spaced that they actually restricted the flow of the Thames, making the water rush through the gaps with dangerous speed. People died shooting the rapids under London Bridge in small boats. The bridge itself caused the river to partially freeze upstream during cold winters because the piers acted almost like a dam. And this brings up a really important point about bridge design that people don't always think about. A bridge doesn't just sit passively over a river. It interacts with the river. The piers obstruct the flow, which changes the water's speed and direction, which causes erosion around the base of the piers, a process called scour. Scour is, to this day, one of the most common reasons bridges fail. The water digs away at the riverbed around the foundations, undermining them, and eventually the pier settles, or tips, and the whole thing comes down. Medieval builders didn't fully understand scour, but they dealt with it instinctively by making their piers as wide and heavy as possible, which ironically made the scour problem worse by blocking more of the river. It's one of those engineering trade-offs that takes centuries to properly sort out. But let's leave the medieval builders for a moment, because something was happening in other parts of the world that we should talk about. While Europe was building its heavy stone arches, China was doing something completely different. Chinese engineers had been building bridges for just as long as anyone, and they developed forms that Europe wouldn't see for centuries. The Zhaozhou Bridge, also called the Anji Bridge, was built around 605 AD by an engineer named Li Chun during the Sui dynasty. It's a single stone arch spanning about 123 feet across the Xiao River in Hebei province. And here's what makes it remarkable. It's a segmental arch, meaning the curve of the arch is less than a full semicircle. It's flatter. A Roman arch is typically a perfect half circle, which means the bridge has to be quite tall relative to its span. Li Chun made his arch much shallower, which meant the bridge deck was nearly level, much easier for carts and people to cross. But a flatter arch generates more outward thrust at its base, which means the abutments have to work harder. Li Chun dealt with this through careful design of the stone structure and, crucially, by including open spandrels, small arches cut into the solid sections above the main arch near the ends. These reduced the bridge's weight, which reduced the thrust, and they also allowed floodwater to pass through during high water instead of pushing against a solid wall of stone. This bridge was built in 605 AD. Europe wouldn't build a comparable segmental arch bridge for another 700 years. Li Chun solved problems that Western engineers hadn't even encountered yet, and the Zhaozhou Bridge is still standing today, more than 1,400 years later, having survived earthquakes, floods, and wars. It's one of the oldest bridges in the world that's still in its original form, and every time I think about it, I'm struck by how much we sometimes underestimate the sophistication of ancient engineering outside the Western tradition. So by the time we reach, say, the 1200s or 1300s, humans have been building bridges for thousands of years, and the basic vocabulary is established. Beams for short spans, arches for longer ones. Stone and wood are the primary materials. The principles of compression and tension are understood intuitively, even if nobody has the mathematical language to describe them precisely yet. Builders learn from experience, from tradition, from watching what works and what falls down. It's empirical engineering, trial and error refined over generations. But something is about to change. As Europe moves toward the Renaissance, a new kind of thinker starts to emerge. Someone who doesn't just build things the way they've always been built, but who asks why they work. Someone who wants to calculate, to predict, to understand the forces inside a structure before it's built, not after it falls down. And this shift from building by tradition to building by analysis, from craft to science, is going to transform everything about how bridges are designed. It's going to open up possibilities that the Roman engineers, brilliant as they were, could never have imagined. One of the first people to really push this boundary was a man you've almost certainly heard of, though probably not in the context of bridges. His name was Leonardo da Vinci, and among the 10,000 other things he was interested in, he spent a surprising amount of time thinking about how structures carry loads. He sketched beams bending under weight. He drew arches and analyzed how forces travel through them. He studied the way columns buckle and how cracks propagate through materials. And what's remarkable about Leonardo in this context isn't that he solved all these problems. He didn't, not really, but that he was asking the right questions in a way that almost nobody else was at the time. He was trying to turn intuition into mathematics. He wanted to know not just that an arch works, but how much load a specific arch of a specific size made of a specific stone could carry before it failed. That's a fundamentally different kind of question than anything the Roman builders were asking, and it's the kind of question that would eventually make modern bridge engineering possible. Leonardo actually proposed a design for a bridge, by the way. A single-span bridge across the Golden Horn in Istanbul, which would have been about 240 meters long. This was around 1502, and he submitted the design to Sultan Bayezid II. It would have been the longest bridge span in the world by a huge margin if it had been built. The design was a flattened arch, elegant and daring, and for centuries people assumed it was just another one of Leonardo's beautiful but impractical fantasies. But in 2001, a Norwegian artist named Vebjørn Sand actually built a scaled version of it as a pedestrian bridge in Norway, and it worked perfectly. The geometry was sound. Leonardo had gotten it right 500 years earlier, working without computers, without structural analysis software, without even a coherent theory of mechanics. Just observation, intuition, and that restless, probing intelligence. But here's the thing. Leonardo was a genius, and geniuses are, almost by definition, not systematic. He filled notebooks with brilliant observations, but he didn't publish them. He didn't create a framework that other people could use. The real transformation of bridge engineering from craft to science required something more methodical, and that took a while longer. The person who probably deserves the most credit for laying the mathematical foundations of structural analysis is Galileo Galilei. Yes, that Galileo, the one with the telescope and the trouble with the Pope. In 1638, near the end of his life, Galileo published a book called Two New Sciences, and one of the two sciences he described was essentially the science of the strength of materials. He asked a beautifully simple question. Why can't you just scale things up? Why can't you take a beam that works at a small size and simply make it bigger to span a longer distance? And the answer he worked out, and this is one of those ideas that sounds obvious once you hear it but is actually quite profound, is that when you double the length of a beam, you don't just double the load it has to carry. The weight increases with volume, which scales as the cube of the dimensions, but the strength of the cross-section only scales as the square. So as things get bigger, they get proportionally weaker. This is why an ant can carry 50 times its own body weight, but an elephant can barely carry itself. It's why you can't just take a bridge design that works at 10 meters and build it at 100 meters. The physics changes with scale. Galileo got some of the details wrong, actually. His analysis of where exactly a beam breaks and how the internal stresses distribute wasn't quite right. But the core insight, that structural behavior is governed by mathematical relationships that change with scale, was revolutionary. It meant that for the first time, you could start to predict whether a structure would stand or fall without actually building it first. Over the next century or so, other thinkers refined and extended these ideas. Robert Hooke, you might remember him from Hooke's Law, which you probably encountered in a physics class at some point, established in 1676 that materials deform in proportion to the force applied to them, up to a point. Stretch a spring twice as hard, it stretches twice as far. Load a beam with twice the weight, it bends twice as much. This linear relationship between force and deformation is the foundation of almost all structural analysis, and it's one of those things that seems so simple you might wonder why it took someone to discover it. But think about what it really means for bridge design. It means that the behavior of a structure under load is predictable. It means you can calculate deflections. It means you can figure out, on paper, how much a bridge will sag under a given weight, and whether that sag is acceptable, and at what point the material will stop springing back and start breaking. Now, around this same period, something else is happening that's going to matter enormously for bridges, and it's not a scientific discovery. It's an economic and social transformation. The Industrial Revolution is beginning to stir in Britain, and with it comes an explosion of demand for transportation infrastructure. Factories need raw materials. Finished goods need to reach markets. Coal needs to move from mines to cities. And all of this movement requires roads, and roads require bridges. And suddenly the old stone arch bridges that had served Europe for centuries aren't enough. They're too slow to build. They can't always span the distances needed. And most critically, the traffic loads are increasing in ways that medieval bridge builders never anticipated. Heavy wagons loaded with iron ore, eventually locomotives. These are forces that demand new solutions. And this is where iron enters the story. Now, humans had been working with iron for thousands of years, obviously, but using iron as a primary structural material for bridges, that was new. And the bridge that marks this transition is one of the most famous structures in engineering history. It's called, simply, the Iron Bridge, and it spans the River Severn at a place called Coalbrookdale in Shropshire, England. It was completed in 1779, and it was the first major bridge in the world built entirely of cast iron. The man behind it was Abraham Darby III. He came from a family of ironmasters who had pioneered the use of coke instead of charcoal for smelting iron, which made iron production much cheaper and more scalable. The bridge was designed primarily by an architect named Thomas Farnolles Pritchard, though Darby oversaw the construction and bore the financial risk, which nearly bankrupted him, by the way. The bridge has a single arch span of about 30 meters, and if you ever see a picture of it, or better yet, if you ever visit, because it's still standing, you'll notice something interesting. The iron members are joined together using techniques borrowed from timber construction. Mortise and tenon joints, dovetails, wedges. The builders didn't yet know how to think about iron on its own terms. They were translating wooden bridge construction into a new material, which is a pattern you see over and over again in engineering history. When a new material arrives, the first generation of designers uses it as if it were the old material, and it takes a while before someone figures out how to exploit what the new material can actually do. And here's what cast iron can do, and what it can't. Cast iron is extremely strong in compression. You can pile enormous weight on a cast iron column and it will hold up beautifully. But cast iron is brittle. It's weak in tension, and it fails suddenly, without warning. You remember how we talked about stone having that same limitation? Strong in compression, weak in tension. Cast iron is better than stone in tension. but it shares that fundamental brittleness. If you overload a cast iron beam, it doesn't bend gracefully and give you a warning. It snaps. And that characteristic is going to cause some terrible bridge failures in the decades ahead. But for the moment, in the late 1700s, iron is exciting. It's the future, and engineers start building iron bridges all over Britain and then across Europe. Thomas Telford, one of the great civil engineers of the era, built hundreds of bridges in the early 1800s, many of them using cast iron arches. Telford was a fascinating figure. He was born into poverty in Scotland, the son of a shepherd who died when Telford was an infant, and he essentially educated himself, working as a stonemason before gradually moving into engineering and architecture. He had an incredible eye for elegant design and a deep practical understanding of materials. He built roads, canals, harbors, churches. But bridges were his great love, and his iron arch bridges across Wales and the Scottish Highlands are still admired for their grace. Telford also built one of the most important early suspension bridges, and this is where the story takes another turn, because suspension bridges represent a completely different approach to spanning distance. Let me explain what I mean. With a beam bridge, the structure resists loads primarily through bending. The beam pushes down, and the material has to resist being bent. With an arch, the loads are converted into compression that flows through the curved shape down into the foundations. But a suspension bridge works on an entirely different principle. You hang the deck, the roadway, from cables, and those cables are draped over tall towers and anchored at each end. The cables are in tension. They're being pulled, not pushed, and the towers are in compression, supporting the weight of the cables and everything hanging from them. So a suspension bridge is this beautiful division of labor. The towers handle the compression, the cables handle the tension, and the deck just has to be stiff enough not to twist or ripple too much in the wind. The basic idea of a suspension bridge is ancient, by the way. People in South America, in the Himalayas, in China, they'd been building rope bridges for centuries, maybe millennia. Vines, woven fibers, later iron chains. But these were narrow, flexible, and terrifying to cross. The modern suspension bridge, one that could carry heavy traffic over long spans, that required iron chains or wire cables, and it required understanding how to manage the enormous forces involved. Telford's Menai suspension bridge, completed in 1826, was a landmark. It connected the island of Anglesey to the mainland of Wales, spanning about 177 meters, with a deck hung from wrought iron chains. Notice I said wrought iron, not cast iron. This distinction matters enormously. Wrought iron is a different material. It's been worked and hammered, which aligns the grain structure and makes it much more ductile, much better in tension. You can pull on wrought iron and it will stretch and deform before it breaks, giving you warning. It's the right material for a suspension cable, where everything is in tension. And this is a perfect example of that principle we keep coming back to, that the material dictates the form. Cast iron, strong in compression, leads naturally to arches. Wrought iron, strong in tension, opens the door to suspension bridges. The material tells you what shapes are possible, and the engineer's job is to listen. But suspension bridges in this early period had a problem, and it was a problem that wouldn't be fully understood for over a century. They moved. They swayed in the wind. They oscillated in ways that could be frightening and occasionally catastrophic. In 1831, just 5 years after the Menai Bridge opened, a suspension bridge over the River Tweed in Scotland collapsed when a gale set it swinging violently. Soldiers marching across a suspension bridge in Angers, France in 1850 caused it to collapse when their rhythmic footsteps matched the bridge's natural frequency. 226 people died. This phenomenon, where an external force synchronizes with a structure's natural vibration and amplifies it, is called resonance. And it's one of the most dangerous things that can happen to a bridge. We're going to come back to resonance later, because it's at the heart of one of the most famous engineering disasters of the 20th century. And the story of how engineers learned to deal with it is really one of the great dramas in all of engineering. But before we get there, we need to talk about what happened in the decades after Telford, because the bridge story is about to accelerate in a way that changes everything. So it's the middle of the 19th century, and the world is being reshaped by one thing above all else: the railroad. And railroads need bridges. Lots of them. But here's the challenge. A railroad bridge is a completely different animal from a road bridge or a footbridge. A locomotive pulling a loaded train is extraordinarily heavy, and that weight is concentrated on the rails, on the wheels, in a way that a crowd of pedestrians or a line of horse-drawn carts just isn't. Plus, trains move fast, and a fast-moving heavy load creates dynamic forces that change over time, that pulse and hammer at the structure with every wheel that rolls across. A bridge that works perfectly well for foot traffic might shake itself apart under a train. And suspension bridges, with all that flexibility, all that sway, they were generally terrible for railroads. You need stiffness. You need a bridge that doesn't move. Enter Robert Stephenson, son of George Stephenson, the famous railway pioneer. Robert was tasked in the 1840s with carrying the Chester and Holyhead Railway across the Menai Strait, essentially the same crossing that Telford had bridged with his suspension design just 20 years earlier. But Stephenson couldn't use a suspension bridge, too flexible for trains. He couldn't build a conventional arch because the Admiralty insisted on maintaining clear headroom for tall ships passing underneath. So he was stuck. He needed something new. What he came up with, working closely with the engineer William Fairbairn and the mathematician Eaton Hodgkinson, was the Britannia Bridge, completed in 1850, and it was unlike anything anyone had ever built. The idea was radical. Instead of hanging the deck from cables or supporting it on arches, Stephenson would build enormous rectangular tubes out of wrought iron, hollow boxes, big enough that the train would run inside them. The tubes themselves were the bridge. They were beams, essentially, but beams of a completely new kind. Massive, riveted wrought iron boxes spanning over 140 meters between the stone towers. Now, what's brilliant about this is the engineering thinking behind it. Fairbairn and Hodgkinson conducted hundreds of experiments on model tubes, testing different cross-sectional shapes, figuring out where the metal needed to be thickest, where it could be thinner. They understood, and this was cutting-edge knowledge at the time, that in a beam under load, the top is in compression and the bottom is in tension. So the design of the tube was asymmetric. More material at the top and bottom, where the stresses were highest, and thinner walls on the sides. They were designing the cross-section to match the stress distribution. This is the birth of what we now call plate girder design, and it's the ancestor of every steel I-beam and box girder you see in modern construction. Every highway overpass you drive under, every steel beam holding up a parking garage, there's a direct line back to Fairbairn's experiments and Stephenson's Britannia tubes. The construction itself was a spectacle. Each tube weighed around 1,500 tons and was assembled on the shore, then floated out on pontoons and hydraulically jacked up into position between the towers. Think about that. floating a 1,500-ton iron tube on the water, maneuvering it into position with the tides, then lifting it meter by meter with hydraulic presses in the 1840s. It's astonishing. And it worked. The Britannia Bridge carried trains across the Menai Strait for over a century, until a fire in 1970 damaged the tubes beyond repair. But the concept it proved, that you could build rigid enclosed beam structures from iron plates and rivets to carry enormous loads over long spans, that concept changed bridge engineering forever. And here's where we need to talk about a material that's about to take over the world: steel. Because wrought iron, as good as it was, had limitations. It was labor-intensive to produce. All that hammering and working to refine the metal. And its properties varied. One batch might be slightly different from the next. What engineers really wanted was something stronger, more consistent, and available in large quantities. And in the 1850s and 1860s, that something arrived. Henry Bessemer patented his converter in 1856, a process that could turn molten pig iron into steel by blowing air through it to burn off excess carbon. The Siemens-Martin open hearth process followed in the 1860s, offering even better control over the steel's composition. Suddenly, steel went from being a rare, expensive material used mainly for tools and weapons to something that could be produced by the ton, affordably, reliably. And steel is remarkable stuff. It's stronger than wrought iron in both tension and compression. It's more uniform. You can roll it into precise shapes, beams, plates, angles, channels, in a factory, then ship those standardized pieces to a construction site and bolt or rivet them together. Steel doesn't just improve bridges, it makes entirely new kinds of bridges possible. The first major steel bridge was the Eads Bridge across the Mississippi River at St. Louis, completed in 1874. James Buchanan Eads was a fascinating character, largely self-educated. He'd made his fortune salvaging wrecked steamboats from the Mississippi riverbed using diving bells he designed himself. He knew that river intimately, knew its currents, knew its treacherous shifting bottom. When he proposed bridging it, the established engineering community was skeptical. Eads had never built a bridge before, but he had something many trained engineers lacked: a deep, practical understanding of the forces he was dealing with, earned through years of working underwater in one of the most powerful rivers on Earth. The Eads Bridge used 3 steel arches, each spanning over 150 meters, and the foundations went down to bedrock through pneumatic caissons, massive pressurized chambers sunk into the riverbed, where workers could excavate in compressed air. This was grueling, dangerous work. Workers suffered from what was then called caisson disease, agonizing joint pain, paralysis, sometimes death, caused by nitrogen bubbles forming in the blood when they returned to normal atmospheric pressure too quickly. We now call it decompression sickness, or the bends. Eads's project saw 14 workers die from it. The cause wasn't understood. At the time, though, Eads noticed that shorter shifts and slower decompression seemed to help, and he adjusted the work schedule accordingly. It was a hard-won lesson, and the same problem would haunt another famous bridge project just a few years later. But the Eads Bridge itself was a triumph. Those steel arches are still carrying traffic today, over 150 years later. And the use of steel was a statement. Eads actually had to fight to use it, because many engineers didn't trust the new material. Andrew Carnegie, who supplied the steel, had to have it rigorously tested to satisfy the doubters. Every batch was checked, and it held up. Steel proved itself at St. Louis, and after that, there was no going back. Now, while Eads was building in St. Louis, something even more ambitious was underway in New York. And this is one of those stories that deserves real time, because it's got everything: visionary engineering, family drama, personal sacrifice, political corruption, and a bridge that became one of the most recognizable structures on Earth. I'm talking about the Brooklyn Bridge. The man behind it was John Augustus Roebling, a German-born engineer who had already built several successful suspension bridges, including one across the Niagara Gorge that actually carried railroad trains, something most engineers thought was impossible for a suspension bridge. Roebling's innovation was to combine the suspension principle with a stiffening truss system and diagonal stay cables that radiated from the towers, creating a web of support that resisted the kind of oscillation and deformation that had plagued earlier suspension designs. He was, in effect, solving the flexibility problem that had made suspension bridges dangerous, and he was doing it through redundancy, multiple overlapping systems of support so that no single element had to carry too much load. Roebling's design for the Brooklyn Bridge was breathtaking in its ambition. A main span of 486 meters, nearly 3 times longer than any suspension bridge that existed at the time. Massive stone towers rising 84 meters above the water. And for the cables, Roebling specified steel wire, not wrought iron chains. Each main cable would be composed of thousands of individual steel wires bundled together, spun in place high above the East River. The total diameter of each cable was about 40 centimeters, and together they could support an enormous load. This wire cable approach is essentially the same technique used in every major suspension bridge built since. Roebling invented the method, but John Roebling never saw his bridge built. In the summer of 1869, while surveying the site, his foot was crushed by a ferry boat against a piling. He refused conventional medical treatment, opting instead for continuous water therapy, a decision that reflected his belief in hydrotherapy, which was popular at the time. He developed tetanus and died 3 weeks later. He was 63. The project passed to his son, Washington Roebling, who was 32 years old and already an accomplished engineer in his own right. Washington had studied bridge construction in Europe and had worked alongside his father on previous projects. He took over with determination, and he oversaw the most dangerous phase of construction, sinking the massive caissons for the tower foundations. These were enormous timber and iron boxes, open at the bottom, pressurized with compressed air to keep the water out, while workers inside dug down through the riverbed to reach stable ground. On the Brooklyn side, bedrock was about 13 meters down. On the Manhattan side, it was much deeper, over 24 meters. And it was in those caissons, in that compressed air, that disaster struck again. Workers suffered terribly from caisson disease, just as they had at St. Louis. Washington Roebling himself spent long hours in the caissons supervising the work, and in 1872, he was struck by a severe case of the bends that left him partially paralyzed with chronic pain, impaired vision, and difficulty speaking. He was essentially an invalid for the remaining 11 years of construction, but he didn't give up the project. From his apartment in Brooklyn Heights, overlooking the construction site, he watched through a telescope and directed the work through detailed written instructions carried to the site by his wife, Emily Warren Roebling. And here's where Emily's story becomes extraordinary, because she didn't just carry messages. She taught herself higher mathematics, cable analysis, stress calculations, materials science. She dealt with suppliers, contractors, politicians. She answered technical questions from the engineers on site. She became, in every practical sense, the field engineer of the Brooklyn Bridge, though she never held the title. When the bridge finally opened on May 24, 1883, Emily Roebling was the first person to cross it, carrying a rooster as a symbol of victory. It's one of the great untold stories in engineering history. A woman who mastered one of the most complex engineering projects of the 19th century, at a time when women were barred from engineering schools. The Brooklyn Bridge itself was a masterpiece, and it demonstrated something important about structural philosophy. Roebling had deliberately overbuilt it. He designed the bridge to be 6 times stronger than it needed to be, because he didn't fully trust the new steel wire, and he wanted enormous margins of safety. That conservatism is why the bridge is still standing today, still carrying traffic over 140 years later, even though the loads it bears are far heavier than anything Roebling imagined. There's a lesson in that. Sometimes the best engineering decision is to admit what you don't know and build in enough margin to cover your ignorance. And the Brooklyn Bridge also showed something about how suspension bridges could be made stable. Those diagonal stay cables radiating from the towers, combined with the stiffening trusses along the deck, they created a structure that was both flexible enough to handle wind and temperature changes and rigid enough to resist dangerous oscillation. Roebling had essentially hybridized 2 structural systems, suspension and cable-stayed, into one bridge. It was elegant, it was redundant, and it worked. But not every engineer who followed would be so careful, and the consequences of forgetting Roebling's lessons about wind and flexibility would be devastating. Absolutely devastating. And the story of how those lessons were lost and then violently relearned is one of the most dramatic episodes in all of engineering history. So let's set the stage. By the early 20th century, suspension bridges were getting longer and longer. Engineers had gotten confident, maybe too confident. Steel was well understood by now, or at least they thought it was. The mathematics of structural analysis had advanced enormously. And there was a kind of aesthetic trend happening in bridge design that would turn out to be deeply dangerous. Bridges were getting slimmer, more elegant. Engineers were shaving away material, making decks thinner, reducing the depth of stiffening trusses, because they could, because the math said the steel was strong enough. And honestly, the bridges looked beautiful. There's something about a long, slender suspension bridge that just appeals to the eye. That ribbon of roadway draped between towers, barely there, almost floating. Designers loved it. The public loved it. And the calculations said it would hold the weight. Here's the thing, though. Holding the weight isn't the only job a bridge has to do. Let me take you to the morning of November 7th, 1940. The place is the Tacoma Narrows, a stretch of water in Puget Sound, Washington State. A brand new suspension bridge spans the Narrows. It opened just 4 months earlier, on July 1st. The main span is about 853 meters, which made it the 3rd longest suspension bridge in the world at the time. And it's gorgeous. Slim, modern, clean lines. The deck is a shallow plate girder design, only about 2.4 meters deep, incredibly shallow for a span that long. For comparison, the Golden Gate Bridge, which opened 3 years earlier with a slightly longer span, has stiffening trusses about 7.6 meters deep. The Tacoma Narrows deck was less than 1/3 of that depth. It was, by any measure, an extraordinarily slender bridge, and from the very first day it was open, it moved. Not a little, a lot. The deck would undulate in the wind, rising and falling in long, rolling waves. Drivers crossing the bridge would see the car ahead of them disappear below a crest, and then reappear. People called it galloping Gertie. Some people thought it was fun, like a roller coaster. Engineers were less amused. But the bridge had been designed by Leon Moisseiff, one of the most respected bridge engineers in America. He'd consulted on the Golden Gate and the Manhattan Bridge, and his deflection theory calculations said the bridge was safe. The vertical oscillations were within acceptable limits, he argued. The structure could handle it. On the morning of November 7th, the wind was blowing at about 67 kilometers per hour. Not a hurricane, not even a particularly severe storm. A stiff wind, the kind the bridge should have handled easily, based on static load calculations. The bridge began its usual vertical oscillations. But then, around 10 in the morning, something changed. The motion shifted. Instead of bouncing up and down symmetrically, the deck began to twist. One side would rise while the other fell. Then they'd reverse. The bridge was no longer just galloping. It was writhing. The torsional oscillation grew and grew, the deck twisting back and forth at increasing angles. Within an hour, the twisting had become so violent that the deck was tilting to angles of about 45 degrees on each side. And then, at about 11 a.m., the bridge tore itself apart. Sections of the deck broke free and plunged into the water below. The center span collapsed entirely. The whole thing was captured on film. A professor named Barney Elliott from a nearby college had been filming the bridge's oscillations for weeks, and his footage of the final collapse became one of the most famous engineering films ever made. You've probably seen it, even if you don't know the name. That grainy black and white footage of a bridge deck twisting and rippling like a ribbon in the wind before breaking apart. That's Galloping Gertie. Now here's what's really important. Nobody died. One person tried to rescue a dog that was stranded in a car on the bridge, but the dog bit him and wouldn't come out, and the dog was the only fatality, which is miraculous, really, given the violence of the collapse. But the real significance of the Tacoma Narrows failure wasn't the human cost, it was the engineering lesson. Because this collapse forced the entire profession to confront something they'd been ignoring, or at least underestimating, for decades. The question was, why did the bridge fail? And the initial popular explanation, the one you'll still hear sometimes, is resonance. The idea that the wind was gusting at exactly the right frequency to match the bridge's natural frequency of oscillation, and the vibrations built up until the structure couldn't take it anymore. It's a neat explanation. It's the tuning fork analogy. Hit the right note and the glass shatters. And it's not entirely wrong, but it's not really right either. The actual mechanism was something more subtle and, in some ways, more frightening. It's called aeroelastic flutter. And to understand it, you need to think about the bridge deck not just as a structure carrying loads, but as an aerodynamic body, like a wing. When wind flows over and around the bridge deck, it doesn't just push on it. It creates complex patterns of pressure, areas of high pressure and low pressure, that depend on the shape of the deck and, crucially, on the angle at which the wind hits it. Now, if the deck is rigid and doesn't move, those pressure patterns are stable. But if the deck starts to twist, even slightly, the angle of the wind relative to the deck changes, and that change in angle changes the pressure pattern. And here's where it gets dangerous. If the new pressure pattern creates a force that pushes the deck further in the direction it's already twisting, you've got a positive feedback loop. The twist creates a force that increases the twist, which creates a larger force, which increases the twist further. The energy isn't coming from resonance with a particular gust frequency. The energy is being extracted continuously from the steady wind. The bridge is essentially pulling energy out of the airflow and converting it into ever larger oscillations. That's flutter. And once it starts, it's self-reinforcing. It doesn't need the wind to gust at a special frequency. It just needs enough wind speed to overcome the structural damping, the bridge's natural tendency to resist twisting. And once that threshold is crossed, the oscillations grow without bound until something breaks. Think about what that means. It means the bridge wasn't destroyed by an unusually strong wind. It was destroyed by a moderate wind interacting with a deck that was the wrong shape. Too shallow, too streamlined in the wrong way, too flexible in torsion. The H-shaped cross-section of the Tacoma Narrows deck, with those shallow plate girders on either side of the roadway, was almost perfectly designed to generate flutter. It was an accidental airfoil, and a badly behaved one at that. And this is where we come back to Roebling and the Brooklyn Bridge. Remember those deep, stiffening trusses? Remember those diagonal stay cables? They made the Brooklyn Bridge enormously resistant to torsional movement. The deck couldn't easily twist because the truss was deep and the stays constrained it. Roebling hadn't known about aeroelastic flutter. The concept wouldn't be formally described for decades. But his conservative instinct to make the bridge rigid against wind forces had protected his structure from exactly this kind of failure. He'd built in resistance to a problem he couldn't even name. Moisseiff, on the other hand, had optimized. He'd made the deck as slim and light as the static calculations allowed. And his deflection theory, which was the standard analytical tool for suspension bridge design at the time, simply didn't account for aerodynamic effects. It treated wind as a static horizontal force. The wind pushes sideways on the bridge. You calculate the deflection. Done. It didn't consider the dynamic interaction between wind and structure, the way the bridge's own movement could change the forces acting on it. The theory was correct as far as it went. It just didn't go far enough. The aftermath of the Tacoma Narrows collapse was a complete revolution in bridge engineering. Almost overnight, the profession realized that aerodynamics mattered, that you couldn't design a long-span bridge without understanding how it would interact with wind as a dynamic system. Wind tunnel testing became standard practice. Bridge decks started being designed not just for strength and stiffness, but for aerodynamic stability. The shallow plate girder deck fell out of favor for long spans, replaced by designs that were either deep enough to resist torsion through brute stiffness, or shaped to be aerodynamically stable, to shed wind smoothly rather than generating flutter. And this is where we see one of the most elegant solutions in modern bridge engineering emerge. If you've ever looked closely at a modern long-span suspension bridge, say, a bridge built in the last 40 or 50 years, you might notice that the deck cross-section looks different from older bridges. Instead of a boxy shape with trusses or girders on the sides, many modern bridges use what's called a streamlined box girder deck. It's a closed, hollow steel box, often with a shape that's almost like a flattened airfoil, tapered at the edges, smooth, with no sharp corners for the wind to catch on. The idea is that wind flows over and around this shape without creating the turbulent pressure patterns that cause flutter. The deck is designed to be aerodynamically transparent, to let the wind pass without extracting energy from it. The person who really pioneered this approach was a German-born British engineer named Fritz Leonhardt, though the concept was developed by many people in the decades after Tacoma Narrows. But one of the most famous early applications was the Severn Bridge in England, which opened in 1966. Its designers, including Gilbert Roberts of the firm Freeman Fox and Partners, used a streamlined steel box girder deck that was remarkably thin and light, but aerodynamically stable. They'd tested it extensively in wind tunnels, and it worked beautifully. The Severn Bridge proved that you could build a long, slender, elegant suspension bridge that was also safe in wind, as long as you got the aerodynamics right. It was a triumph of understanding over brute force. Instead of making the bridge heavier and stiffer to resist wind, you made it the right shape so the wind wasn't a problem in the first place. Now, the box girder concept was brilliant, but it came with its own growing pains. And this is a part of the story that doesn't get told as often. But it's important because it shows how even good ideas can go wrong when they're pushed too far too fast. In the late 1960s and early 1970s, steel box girder bridges became enormously popular, not just for suspension bridges, but for shorter span highway bridges too. They were economical. They looked clean and modern, and engineers loved working with them. But the construction process for these bridges involved assembling large steel box sections and cantilevering them out from piers, building the bridge outward from each support until the sections met in the middle. And during that construction phase, before the bridge was complete and all the structural elements were connected, the partially built cantilevers were vulnerable. The steel plates were thin, the box sections were under enormous stress from their own weight, and if anything went wrong with the alignment or the temporary supports, you could get a buckling failure. The thin steel walls of the box would just fold, almost like crushing a cardboard tube. And that's exactly what started happening. The first major disaster struck on October 15th, 1970, in Milford Haven, Wales. A box girder bridge being built over the estuary there, it was actually quite close to the Severn Bridge, geographically speaking, which is a bitter irony, collapsed during construction. The bridge was being built by the cantilever method, pushing out from the piers, and one of the box girder sections buckled. 4 workers were killed. The bridge was designed by, of all firms, Freeman Fox and Partners, the same firm behind the elegant Severn Bridge, and the investigation revealed problems with the way the steel plates had been stiffened, or rather, hadn't been stiffened enough. The diaphragms inside the box, the internal walls that were supposed to keep the cross-section from distorting, weren't adequate for the stresses during construction. But here's what's really troubling. Just a few months later, on November 2nd, 1970, another box girder bridge collapsed during construction. This one was in Melbourne, Australia, the Westgate Bridge spanning the Yarra River. And this was far worse. A large section of the steel box girder deck buckled and fell while workers were on it and beneath it. 35 people died. 35. It remains one of the worst construction disasters in Australian history. The causes were complex, but at the heart of it was a problem with how the two halves of a box section were being joined. The two halves didn't quite match. There was a difference in camber, a slight bow in the steel, and the construction team had tried to force them together by removing bolts from a temporary connection to let one side drop down and meet the other. When they did that, the thin steel plate buckled catastrophically. The section that fell was about 112 meters long and weighed around 2,000 tons. It dropped like a stone. And then, less than a year later, in November 1971, yet another box girder bridge collapsed during construction, this time in Koblenz, Germany, a bridge over the Rhine. 13 workers died. Same basic problem. Buckling of thin steel plates in the box girder during the cantilever construction phase. 3 collapses in barely a year. 52 people dead. All box girder bridges. All during construction. All involving buckling of thin steel plates. This was a crisis, and the engineering profession knew it. In the UK, the government appointed a committee led by a man named Marrison, the Marrison Committee, to investigate the whole issue of box girder bridge design and construction. They essentially halted construction on box girder bridges across Britain until the problems were understood. And what the Marrison inquiry found was that the design rules engineers had been using for thin steel plates and compression were inadequate. The theoretical understanding of plate buckling existed. It had been studied since the early 20th century. But the practical design codes hadn't kept pace with how aggressively engineers were using thin plates in these new box girder designs. The codes assumed certain idealized conditions that didn't match reality on a construction site. Perfectly flat plates, perfectly uniform loads, no imperfections. Real steel plates have slight waviness, residual stresses from welding, small misalignments, and in the real world, those imperfections can trigger buckling at loads well below what the idealized theory predicts. So the profession had to step back and essentially rewrite the rules for steel box girder design. New, more conservative design standards were developed. Construction procedures were tightened. And the lesson, once again, was that understanding a concept in theory is not the same as understanding it in practice. The box girder is a wonderful structural form. It's still used everywhere today. But those collapses in 1970 and 1971 were a painful reminder that when you push a new technology quickly, when you scale it up and spread it around before you've fully understood its failure modes, people can die. It's the same pattern we saw with early suspension bridges, with cast iron, with the Tacoma Narrows. Innovation outruns understanding, and the bridge teaches you what you missed. Let's take a breath from that and talk about something that might seem unrelated, but actually connects to everything we've been discussing. Let's talk about concrete. Specifically, reinforced concrete and then pre-stressed concrete. Because these materials transformed bridge engineering in the 20th century in ways that are just as profound as the shift from iron to steel. Now, you already know about concrete from the Romans, that incredible pozzolanic mix they used to build the Pont de Garde and the Pantheon. But Roman concrete, as good as it was, had the same fundamental limitation as stone. It's strong in compression, but weak in tension. You can stack it, you can build arches with it, but you can't span a gap with a flat concrete beam very effectively because the bottom of that beam is in tension and concrete cracks and fails in tension. For centuries after the Romans, concrete was largely forgotten in Europe, and when it came back in the 18th and 19th centuries, it came back with the same limitation. Here's the thing that changed everything. In the mid-1800s, people started experimenting with embedding iron, and later steel, bars inside concrete. The idea is beautifully simple. Concrete is great in compression. Steel is great in tension. If you put steel bars in the parts of the concrete that are going to experience tension, the steel carries those tensile forces, while the concrete carries the compressive ones. They work together. And it works remarkably well because concrete and steel happen to have almost the same coefficient of thermal expansion. They expand and contract at nearly the same rate when temperature changes, so they don't tear themselves apart as the seasons shift. That's a lucky coincidence of materials science, and it's one of those things that makes you wonder what bridge engineering would look like if that coincidence didn't exist. A French gardener named Joseph Monnier is often credited with popularizing reinforced concrete in the 1860s and 1870s. He was making garden pots and tubs with iron mesh embedded in concrete and realized the combination was far stronger than either material alone. But the real engineering development of reinforced concrete for structures came from people like François Hennebique, also French, who in the 1890s developed a comprehensive system for reinforced concrete construction. Beams, columns, slabs, all working together as a monolithic frame. Hennebeek was a brilliant self-promoter too. He built demonstration structures, published newsletters, licensed his system to contractors across Europe. By the early 1900s, reinforced concrete was everywhere. For bridges, reinforced concrete opened up new possibilities. You could build arch bridges in concrete that were lighter and cheaper than stone. You could build beam bridges that actually worked over reasonable spans because the steel reinforcement handled the tension. The Swiss engineer Robert Maillart took reinforced concrete bridge design to an art form in the early 20th century. His bridges in the Swiss Alps, like the Salzgitter Bridge, completed in 1930, are stunningly beautiful. The Salzgitter is a three-hinged concrete arch spanning a deep gorge, and Maillart designed it with a hollow box cross-section that was incredibly thin and efficient. He understood that concrete didn't have to be massive and heavy. He treated it almost like a sculptural medium, shaping it to follow the flow of forces. Engineers and architects still study his bridges today, and the Salzgitter has been called one of the most beautiful bridges in the world. It's also a reminder that engineering and aesthetics aren't enemies. When a structure is shaped honestly by the forces it carries, it often ends up being beautiful, almost by accident. But reinforced concrete has a limitation. The steel reinforcement only kicks in after the concrete has cracked in tension. The cracks have to open up slightly before the steel starts carrying load. For many applications, that's fine, but for longer spans, those cracks can be a problem. They let in water and salt, which corrode the steel, which causes the concrete to spall and deteriorate. And the spans you could achieve with ordinary reinforced concrete were limited because the concrete's own weight became the dominant load. This is where a French engineer named Eugène Freycinet enters the story, and what he figured out was genuinely one of the most important ideas in the history of structural engineering. Freycinet had been working with concrete since the early 1900s, and he'd noticed something that bothered him. Concrete creeps. It slowly deforms under sustained load. He studied this phenomenon carefully, and that deep understanding of how concrete actually behaves led him to develop the practical system for pre-stressed concrete. The idea of pre-stressing had been proposed by others before him, but Freycinet made it work reliably, starting in the 1930s and really perfecting it in the 1940s. Here's the concept, and it's so clever. Imagine you have a row of books standing upright on a shelf, and you want to lift the whole row at once. If you just try to pick them up from underneath, they'll fall apart. There's nothing holding them together. But if you squeeze the row tightly from both ends, pressing the books together with your hands, you can lift the entire row as a single unit. The compression from your hands creates enough friction and internal pressure that the books act as one solid beam. That's pre-stressing. You're putting the concrete into compression before it ever has to carry a load, so that when loads do come along and try to put parts of the concrete into tension, they first have to overcome all that built-in compression. If you pre-stress enough, the concrete never actually goes into net tension at all. No tension means no cracks. No cracks means no water getting in. No water means no corrosion. And because you're using the material so much more efficiently, you can span much longer distances with much less material. Freycinet's method involved threading high-strength steel cables, called tendons, through ducts in the concrete, then stretching those tendons with hydraulic jacks after the concrete had hardened and anchoring them at the ends. The stretched tendons try to spring back to their original length, and in doing so, they squeeze the concrete into compression. It's like a permanent, built-in hug that holds the whole structure together. And the beauty of it is that you can control exactly where and how much compression you apply. You can curve the tendons so they provide more pre-stress where it's needed most, at the bottom of the beam at mid-span, for instance, where tension would normally be greatest. Freycinet demonstrated his ideas dramatically in 1934 when he saved the Le Havre Maritime Station in France from collapse. The building's foundations were settling, and the structure was in danger. Freycinet used pre-stressed concrete jacks to stabilize it, proving the practical power of his techniques. But it was after World War II that pre-stressed concrete really took off for bridges. Europe needed to rebuild thousands of destroyed bridges quickly and economically, and pre-stressed concrete was perfect for the job. It used less steel than reinforced concrete, which mattered enormously when steel was scarce, and it could be precast in factories and assembled on site. Freycinet himself designed several notable bridges, and his ideas spread rapidly through engineers like Gustave Magnel in Belgium and Waguillon in France, who wrote textbooks that trained a whole generation. And this is where the technique called segmental construction comes in, which is one of the most elegant construction methods ever devised for bridges. Instead of building a bridge by pouring concrete in place over enormous temporary scaffolding, which is expensive and sometimes impossible over deep valleys or busy waterways, you cast the bridge in short segments, maybe 3 or 4 meters long each, either at a factory or right there at the bridge site. Then you assemble those segments one at a time, gluing them together with epoxy and threading pre-stressing tendons through all of them to squeeze the whole assembly into one continuous monolithic beam. You can build outward from a pier in both directions simultaneously, balancing the weight, adding one segment at a time, stressing new tendons as you go. The bridge grows outward like 2 arms reaching from each pier until they meet the arms coming from the next pier, and the whole time, the pre-stressing tendons are holding everything together, keeping every joint in compression so nothing can pull apart. Jean Muller, a French engineer who had worked with Freycinet, became one of the great pioneers of segmental construction, and the bridges he designed using this method are among the most impressive concrete structures anywhere in the world. His Long Key Bridge in the Florida Keys, completed in 1982, stretches over 18 kilometers of open ocean using precast segmental construction. Hundreds of box-shaped concrete segments, each one cast on shore, barged out to position, lifted into place by a launching gantry, glued to the previous segment with epoxy, and then post-tensioned into a continuous ribbon of pre-stressed concrete hovering over the turquoise water. It's a remarkable thing when you think about it. Each segment by itself is just a hollow concrete box, maybe weighing 60 or 70 tons, and it can't do much on its own. But thread those steel tendons through all of them and tension them up, and suddenly you've got a bridge that can carry traffic for decades over salt water in hurricane country. And Muller didn't stop there. He refined the method throughout his career, working on bridges all over the world, in France, in Southeast Asia, in the United States. He developed what's called the span-by-span method, where instead of building outward from piers in a balanced cantilever, you assemble an entire span's worth of segments on a movable scaffolding truss underneath, stress them all together, then slide the truss forward to the next span and do it again. It's like a bridge-building machine that inches its way across the landscape, leaving finished bridge behind it. The speed this allows is extraordinary. On some projects, crews were completing a full span every few days. Now, here's the thing about segmental construction that makes it so relevant to modern bridge building. It separates the two hardest parts of the job, making the concrete and putting it in place, and lets you optimize each one independently. When you cast segments in a factory or a casting yard, you control the conditions precisely. The concrete is mixed to exact specifications. The forms are reused hundreds of times, so every segment matches the one before it, and quality control is much easier than when you're pouring concrete 100 feet in the air on a windy day. Then the assembly in the field becomes more like a logistics problem. How do you get the right segment to the right place at the right time and connect it properly? It turns bridge building into something almost industrial, almost like manufacturing. And that's a profound shift from the old days of building everything in place. But let's zoom out for a moment, because while segmental pre-stressed concrete was transforming medium and long-span bridges in the second half of the 20th century, something else was happening at the very longest spans. And this brings us to cable-stayed bridges, which are arguably the most visually dramatic bridge type in the modern world and have an engineering story that's really worth spending some time on. You already know suspension bridges, the Brooklyn Bridge, the Golden Gate, the ones with the big sweeping main cables draped between towers with vertical hangers dropping down to support the deck. Cable-stayed bridges look superficially similar because they also have towers and cables, but the structural principle is fundamentally different, and understanding that difference tells you a lot about how engineers think about force paths. In a suspension bridge, the main cables are continuous curves running from anchorage to anchorage, passing over the tower tops. The deck hangs from these cables on vertical or near vertical hangers. The cables are in pure tension, the towers are in pure compression, and the horizontal pull of the cables has to be resisted by massive anchorages at each end. Those enormous concrete blocks buried in the ground that you might have noticed if you've ever walked near the end of a big suspension bridge. The forces flow from the deck, up through the hangers, into the main cable, along the cable to the towers and anchorages, and down into the earth. It's an elegant system, but those anchorages are expensive, and the main cables require specialized spinning or prefabrication. A cable-stayed bridge does something cleverer in some ways. The cables run directly from the towers to the deck. No main cable, no hangers. Each cable is a straight line from a point on the tower to a point on the deck, and it supports the deck right where it connects. Think of it like a series of diagonal guy wires holding the deck up from the tower. And here's what's really neat about the geometry. Because the cables come in from both sides of the tower, the horizontal components of their tension forces largely cancel each other out. A cable pulling the deck up on the left side of the tower has a horizontal component pulling the tower to the left, but there's a matching cable on the right side pulling the tower to the right by roughly the same amount. The tower ends up primarily in compression, pushed straight down, and you don't need those giant anchorages at all. The bridge is essentially self-anchored. The deck itself acts as a compression strut, absorbing whatever horizontal forces remain. This makes cable-stayed bridges incredibly efficient for a certain range of spans, roughly 200 to about 1,000 meters. Below that range, simpler beam or arch bridges are usually more economical. Above it, suspension bridges still reign because the cable-stayed geometry starts requiring impossibly stiff decks and enormous towers. But in that sweet spot, cable-stayed bridges are hard to beat. They use less cable than suspension bridges. They don't need anchorages. The towers can be simpler, and they can be built by cantilevering outward from the towers, adding deck segments and cables as you go. Which, if that sounds familiar, it should, because it's conceptually similar to the segmental cantilever method we were just talking about for concrete bridges. In fact, many modern cable-stayed bridges use precast concrete segmental decks supported by stay cables. The techniques feed into each other. The idea of cable-stayed bridges isn't new. You can find sketches going back centuries. There's a famous one by a Croatian inventor named Fausto Verancio from 1595, showing a bridge supported by diagonal chains from towers. And there were a few early attempts in the 18th and 19th centuries, but they mostly failed or were replaced, partly because the materials weren't up to the task, and partly because engineers didn't yet have the analytical tools to design them properly. The cables in a cable-stayed bridge interact with each other and with the deck in complex ways. It's what engineers call a highly statically indeterminate structure, meaning you can't figure out the forces just from simple equilibrium equations. You need to account for how everything deforms together, which requires serious mathematical analysis. It was really in the 1950s that cable-stayed bridges had their modern birth, and it happened in Germany. For the same reason, pre-stressed concrete took off. Post-war reconstruction. German engineers needed to replace destroyed Rhine crossings quickly and economically, and several of them, most notably Fritz Leonhardt, saw the potential of the cable-stayed form. Leonhardt was one of the great structural engineers of the 20th century, a man who combined deep theoretical understanding with practical design genius. He designed the Theodor Heuss Bridge in Düsseldorf, completed in 1957, which is often cited as one of the first modern cable-stayed bridges. It used a relatively small number of widely spaced cables in a fan arrangement radiating from the tower top, and it worked beautifully. But Leonhardt kept refining the concept. He realized that instead of using a few large cables spaced far apart, which concentrates huge forces at a few points on the deck and requires a very stiff, heavy deck girder to span between those points, you could use many smaller cables spaced closely together. This distributes the support more evenly along the deck, so the deck can be much lighter and more slender. It's the difference between holding up a clothesline at 2 points versus holding it up at 20 points. With more supports, the line doesn't sag as much between them, and it doesn't need to be as strong. This multi-cable approach, sometimes called the harp pattern when the cables are parallel, or the fan pattern when they converge at the tower top, became the standard for modern cable-stayed bridges, and is one of the reasons they look so graceful. All those cables fanning out from the tower create that distinctive visual signature you've probably seen on bridges in cities around the world. And the spans kept growing. Through the 70s, 80s, and 90s, cable-stayed bridges pushed longer and longer. The Pont de Normandie in France, completed in 1995, reached 856 meters. Then the Tatara Bridge in Japan hit 890 meters in 1999. And then, in 2012, the Russky Bridge in Vladivostok, Russia, stretched to 1,104 meters, over a kilometer of main span, held up by cables radiating from 2 towers that rise 321 meters above the water. That's taller than the Eiffel Tower. And the deck, despite spanning that enormous distance, is a relatively slender steel box girder, kept in shape by the constant support of those stay cables. Now, what makes these long cable-stayed spans possible is partly materials, modern high-strength steel for the cables and the towers, advanced concrete or steel for the decks, but it's also computation. And this is something worth pausing on, because the role of computers in bridge engineering is one of those quiet revolutions that changed everything without most people noticing. Think back to the engineers we've talked about throughout this story. Galileo working out beam bending with geometry and intuition. The Roeblings calculating cable forces for the Brooklyn Bridge with hand calculations and tables. The designers of the Tacoma Narrows having no real way to model aeroelastic flutter before it happened. For most of engineering history, analysis was done by hand or with simple physical models, and the complexity of what you could design was fundamentally limited by the complexity of what you could calculate. A structure with 3 cables is manageable by hand. A structure with 200 cables, each one interacting with every other cable and with the deck and the towers, where temperature changes and traffic loads and wind gusts all shift the forces around in real time. That's a problem with thousands of equations that need to be solved simultaneously. The finite element method, which emerged in the 1950s and 1960s and became practical with digital computers, changed all of that. The basic idea is beautifully simple, even though the execution can be enormously complex. You take your bridge, this complicated, continuous, 3-dimensional thing, and you divide it into thousands or millions of small, simple pieces called elements. Each element might be a short segment of beam, a small triangle of plate, a single cable. For each element, the physics is straightforward. You know how a short beam bends, how a plate deforms, how a cable stretches. You write equations for each element, then you connect all the elements together by requiring that where they join, the displacements and forces match up. This gives you an enormous system of simultaneous equations, and you feed the whole thing to a computer. Out comes the deformed shape of the bridge, the stresses in every component, the reactions at every support. What this means in practice is that modern bridge engineers can test their designs virtually before a single ton of concrete is poured. They can simulate the bridge being built stage by stage. Because remember, the forces in a bridge during construction are often completely different from the forces in the finished structure. A cantilever arm reaching out from a pier with only half the cables installed experiences stresses that the completed bridge will never see. Getting the construction sequence right is as important as getting the final design right, and finite element analysis lets engineers model every intermediate stage. They can simulate wind from every direction, earthquake shaking at various frequencies, thermal expansion on a hot summer afternoon, the slow creep of concrete under sustained load over decades. They can ask what-if questions. What if this cable breaks? What if the foundation settles unevenly? What if the temperature drops 30 degrees overnight? And see the answers in minutes instead of months. And this computational power hasn't just made bridges safer, it's made them more efficient, because engineers can trim away unnecessary material with confidence, knowing exactly where the stresses are and aren't. The result is bridges that are lighter, more elegant, and use fewer resources than their predecessors while carrying heavier loads over longer spans. But computation also introduced a new kind of risk, one that older engineers sometimes worry about. When you can model anything, there's a temptation to trust the model completely, to forget that the model is only as good as the assumptions that went into it. Remember the box girder crisis. Those bridges collapsed partly because the theoretical analysis assumed perfect plates, and real plates have imperfections. A finite element model will give you beautiful, precise-looking numbers, but if you've made a wrong assumption about the material properties, or the boundary conditions, or the load combinations, those numbers can be beautifully, precisely wrong. The best modern bridge engineers use computation as a powerful tool, but maintain a healthy skepticism, cross-checking results against simpler hand calculations, against physical intuition, against the hard lessons of history. And some of the most important lessons in that history came from failures that no one saw coming. Failures that revealed gaps not just in calculation, but in fundamental understanding. Which brings us to something that happened in Minneapolis on a warm August evening in 2007, when a bridge that had carried traffic reliably for 40 years suddenly, without any warning at all, dropped into the Mississippi River during the evening rush hour. The I-35W bridge was nothing exotic. It wasn't a record-breaking span. It wasn't a daring experiment in new materials or a showcase for some novel structural form. It was a steel-deck truss bridge, the kind of workhorse structure you'll find carrying interstate highways all across the United States. It opened in 1967. It carried about 140,000 vehicles a day across the river in downtown Minneapolis, and for most of its life, nobody thought much about it. It was just there, doing its job, part of the background of daily life. And that ordinariness is exactly what made its collapse so unsettling, because if a perfectly normal bridge on a perfectly normal highway could just fall down one evening, what did that say about all the other perfectly normal bridges people were driving over every single day? Here's what happened. On August 1st, 2007, around 6 in the evening, the bridge was carrying bumper-to-bumper rush hour traffic. There was also a construction project underway on the deck surface. Workers were resurfacing the roadway, and they'd stockpiled piles of sand and gravel and other construction materials on the bridge. At 6:05 p.m., the center span of the bridge fractured and collapsed, falling about 115 feet into the river and onto the riverbanks below. 13 people died. 145 were injured. School buses, cars, trucks, construction equipment. Everything on that center section went down together. The collapse took roughly 4 seconds from start to finish. Now, the investigation that followed was one of the most thorough bridge failure analyses ever conducted. The National Transportation Safety Board spent over a year examining every piece of evidence. The wreckage pulled from the river, the maintenance records going back decades, the original design calculations from the 1960s, the construction loads that were on the bridge that day. And what they found was a story about something subtle and deeply troubling, a failure that had been built into the bridge from the very beginning, but that took 40 years to finally matter. The critical components were called gusset plates. And let me explain what those are, because they're important, and they're the kind of thing most people never think about. A truss bridge, you'll remember from way back at the beginning of our conversation, works by breaking a structure into triangles. You have these long steel members, some in compression, some in tension, arranged in triangular patterns so that loads get distributed efficiently. But here's the thing. Those individual members have to connect to each other somewhere. At the joints, where multiple members converge, you need some way to tie everything together. That's what a gusset plate does. It's a flat steel plate, usually roughly triangular or trapezoidal in shape, and the ends of the truss members are bolted or riveted to it. Think of it like the hub of a wheel where the spokes meet. The gusset plate transfers forces from one member to the next, and it has to be strong enough to handle all the forces flowing through that junction simultaneously. On the I-35W bridge, the original designers back in the early 1960s undersized several critical gusset plates. They made them too thin. The plates at certain nodes, particularly the ones called U10, the upper chord nodes near the center of the main span, were about half an inch thick when they should have been roughly twice that. And here's what's remarkable and a little bit heartbreaking about this. It appears to have been a simple design error, not a revolutionary misunderstanding of structural theory, Not some exotic failure mode nobody had ever imagined. Just someone got the calculation wrong or didn't do the calculation at all for those particular plates, and the error was never caught. Not during design review, not during construction inspection, not during the decades of routine inspections that followed. Think about what that means for a second. This bridge was inspected regularly throughout its life. Inspectors walked it, looked at it, filed reports. And starting in the early 1990s, those inspections actually flagged problems: corrosion, fatigue cracking in some members, bowing of certain gusset plates. The bridge was given a structurally deficient rating, which sounds alarming, but which actually applied to tens of thousands of bridges across the country. It meant the bridge needed attention and monitoring, not that it was about to fall down. But nobody went back and rechecked the original gusset plate design. Nobody ran the numbers again to see whether those plates, even when they were brand new, had adequate capacity. The assumption was that the original design was sound and that the issue was deterioration over time. And that assumption was wrong. What actually happened on that August evening was that the additional weight of the construction material stockpiled on the bridge, combined with the rush hour traffic, pushed the load on those already undersized gusset plates past their capacity. The plates at the U10 nodes buckled, and once they buckled, the forces that had been flowing through that joint had nowhere to go. The truss members shifted, adjacent connections failed in rapid succession, and the entire center span lost its structural integrity in seconds. It's a cascade failure. One component gives way, which overloads the next component, which overloads the next, and the whole thing unzips before anyone can even understand what's happening. The I-35W collapse changed how America thought about its infrastructure. It forced a national conversation about the fact that bridges age, that inspection alone isn't enough if you're not asking the right questions, and that tens of thousands of bridges across the country were carrying loads they were never designed for, because traffic volumes and truck weights had increased enormously since the 1950s and 60s, when many of these bridges were built. Congress allocated emergency funding, states accelerated inspection programs, and the engineering profession took a hard look at whether its inspection methods were adequate, whether visual inspection could catch the kind of hidden deficiency that brought down the I-35W bridge, or whether more analytical approaches were needed. And this connects directly to everything we've been talking about with computation and finite element analysis. After the collapse, investigators used finite element models to reconstruct exactly what happened, to identify which gusset plates failed first and how the collapse propagated. Those models were invaluable for understanding the failure. But the cruel irony is that if someone had built a finite element model of the bridge before the collapse and included accurate representations of those gusset plates, the vulnerability would have been obvious. The model would have shown stresses in those plates far beyond what they could handle. The technology to find the problem existed. What was missing was the decision to apply it, the institutional practice of going back and reanalyzing older structures with modern tools. So here's where we are in the story of bridges. We've gone from stone arches built by Roman legions to steel trusses designed by computer, from intuitive rules of thumb to sophisticated mathematical models, and the fundamental challenge hasn't really changed. It's still about understanding forces, about making sure every single component in a structure can handle the loads it will actually experience, and about maintaining that understanding over the entire life of the bridge, not just the day it opens, but decades later when the loads have changed, the materials have aged, and the people who designed it have long since retired. And this brings us to something that's happening right now, in our own time. that represents maybe the most exciting development in bridge engineering since pre-stressed concrete. It's the idea of bridges that can tell you how they're doing. Bridges that are instrumented with sensors, dozens or hundreds or even thousands of them, embedded in the concrete, bonded to the steel, strung along the cables, continuously measuring strain, vibration, temperature, displacement, corrosion, tilt. This is called structural health monitoring, and it's transforming the relationship between engineers and the bridges they're responsible for. The concept is beautifully simple. Instead of sending an inspector out once every 2 years to walk a bridge and look for visible problems, cracks you can see, rust you can touch, deflections you can measure with a tape, you install sensors that watch the bridge continuously, 24 hours a day, 7 days a week. Fiber optic sensors can detect strain changes smaller than a millionth of a meter. Accelerometers can pick up shifts in a bridge's natural vibration frequency that indicate something has changed in its stiffness. Maybe a cable has lost tension. Maybe a bearing has frozen. Maybe a crack has started propagating somewhere you can't see. GPS receivers mounted on towers and decks can track movements to within a few millimeters. The data streams in constantly, and software analyzes it in real time, comparing what the bridge is actually doing to what the models predict it should be doing. If something diverges, if a particular sensor starts reading higher strains than expected, if the bridge's natural frequency shifts slightly, that's a flag. It doesn't necessarily mean something is wrong, but it means something has changed, and an engineer should look into it. The Millau Viaduct in southern France, which we should talk about because it's one of the most extraordinary bridges on Earth, is a perfect example. This is a cable-stayed bridge that carries the A75 motorway across the Tarn Valley, and when it opened in 2004, it was the tallest bridge in the world. Its highest mast reaches 343 meters above the valley floor, taller than the Eiffel Tower. It was designed by the French structural engineer Michel Virlogueux, with the architect Norman Foster shaping its elegant appearance, and it's equipped with an extensive monitoring system that tracks everything from cable tensions to wind speeds to the thermal expansion of the deck. The bridge essentially reports on its own health. And this is where the story of bridges starts to merge with the story of data science, of machine learning, of the Internet of Things, because when you have thousands of sensors generating millions of data points, the challenge shifts from not having enough information to having so much information that you need algorithms to make sense of it. Pattern recognition, anomaly detection, predictive modeling. These are the tools that are starting to define the next era of bridge engineering. Not just building bridges, not just inspecting them, but listening to them continuously, the way a doctor might monitor a patient's vital signs. Some researchers are even working on self-healing materials. Concrete that contains capsules of healing agent or bacteria that produce limestone, so that when a crack forms, the healing mechanism activates and seals it before water and salt can get in and start corroding the reinforcement. It sounds almost like science fiction, but small-scale demonstrations have already shown it works. The bridge of the future might not just tell you when something is wrong. It might fix itself before the problem becomes serious. And speaking of the future, there's one more thread I want to follow, because it ties together so many of the themes we've been exploring tonight. It's the question of what the longest possible bridge span is, and whether there's a fundamental limit to how far we can reach across open water or open air with a single structure. Because right now, the longest bridge spans in the world are suspension bridges, and the current record holder is the 1915 Çanakkale Bridge in Turkey, which opened in March of 2022 and stretches its main span across 2,023 meters of open water. That number chosen deliberately to mark the centennial of the Turkish Republic in 2023. 2,023 meters. That's over 1.25 miles between the two towers, and when you stand beneath one of those towers and look up, you're looking at a structure that rises 318 meters above the water, taller than the Eiffel Tower. The cables that drape between those towers and hold up the deck are carrying enormous loads, and the deck itself is a streamlined steel box girder. Because of course it is. Because after Tacoma Narrows, after the Severn Bridge innovations, after everything we've talked about tonight, that aerodynamic profile is now standard practice for long-span suspension bridges. The wind doesn't push the 1915 Sonic-Haley around. It was designed for it. But here's the thing that fascinates me about this particular bridge, and about the question of maximum span in general. 2,000 meters is extraordinary, but engineers have been sketching bridges with even longer spans for decades. The Messina Strait crossing between Sicily and mainland Italy has been discussed, debated, funded, defunded, and redesigned more times than anyone can count, and the proposed span there is about 3,300 meters, over 3 kilometers in a single leap. That's more than 50% longer than the current record. Can it be done? And if so, what's stopping us? Is there some hard physical limit where a bridge just can't hold itself up anymore? The answer is surprisingly nuanced, and it comes back to something we touched on way back at the beginning of tonight's journey: the relationship between a material's strength and its own weight. Remember when we talked about simple beam bridges and how the beam eventually fails under its own weight as you make it longer? The same principle applies to every bridge type, including suspension bridges. The cables are the critical element. As you increase the span, you need longer cables, and longer cables are heavier, and heavier cables need to support not just the deck and the traffic, but also themselves. At some point, the cable becomes so long and so heavy that it can't even support its own weight, let alone anything else. That's your theoretical limit. For high-strength steel wire, the kind used in modern suspension bridge cables, that theoretical maximum span works out to somewhere around 5,000 to 6,000 meters, depending on the specific grade of steel and the safety factors you apply. So, in principle, a 3,300-meter span across the Messina Strait is within the realm of what steel can do. It's aggressive, it's pushing toward the edge of the envelope, but it's not physically impossible. The challenges are more practical. The seismic activity in that region is intense, the currents in the strait are fierce, the political will has wavered for decades, and the cost estimates keep climbing. But the material science says it could work. Now, here's where it gets really interesting. What if you don't use steel? What if you use something stronger and lighter? Because that ratio, strength to weight, or what engineers call specific strength, is the whole game when it comes to maximum span. And there are materials out there with specific strengths that make steel look almost primitive. Carbon fiber, for instance, has a specific strength roughly 10 times that of steel. In theory, a suspension bridge with carbon fiber cables could span something like 15 to 20 kilometers. That's not a typo. 15 to 20 kilometers in a single span. You could bridge the English Channel. Well, not quite. It's about 34 kilometers at its narrowest, but you could get halfway there with one span, which is a sentence that would have made John Roebling's head spin. Of course, theory and practice are different countries, and the border crossing is expensive. Carbon fiber cables at the scale needed for a major bridge don't exist yet. The manufacturing challenges are enormous. You need to produce incredibly long, consistent, defect-free fibers and bundle them into cables that can be anchored and tensioned reliably over decades. Carbon fiber is also more brittle than steel, which means it doesn't give you the same warning before failure. Steel stretches before it breaks. It yields. It deforms. It tells you something is wrong. Carbon fiber tends to just snap. That's a significant concern for a structure that needs to last 100 years in a harsh environment. And then there's the question of fatigue. How does the material behave under millions of cycles of loading and unloading as traffic crosses and wind blows and temperature changes? We have over a century of data on how steel behaves under fatigue. For carbon fiber at bridge scale, we have almost none. But researchers are working on it. Laboratories in Switzerland, in Japan, in China are testing carbon fiber reinforced polymer cables under simulated bridge conditions, and some of the early results are genuinely promising. There's a pedestrian bridge in Germany, the Stronger Bridge, completed around 2020 as a research demonstrator, that uses carbon fiber reinforced polymer cables. It's small, it's a proof of concept, but it works. And that's how these things always start, right? Think about iron. Abraham Darby's bridge at Coalbrookdale in 1779 was a proof of concept too, a modest span over the Severn built to show that iron could do what stone did. And within a few decades, iron was everywhere. Steel followed the same pattern. Pre-stressed concrete followed the same pattern. Every material revolution in bridge engineering starts with someone building something small and saying, "Look, this works." So maybe in 50 years, maybe in 100, the longest bridges in the world will have cables made of carbon fiber or some material we haven't even developed yet. And the spans will be extraordinary, crossing straits and fjords and channels that today require tunnels or ferries. The fundamental engineering principles won't change, though. The forces still need to go somewhere. Tension, compression, shear, they're eternal. You're just finding new ways to carry them, new materials to carry them through, new geometries to direct them along. And that's really the deep story of bridge engineering, isn't it? It's the same problem, over and over, at every scale and in every era. You have a gap. You need to get across. The forces of gravity are pulling everything down, and you need to find a path for those forces to travel from the deck, through the structure, into the ground. The Romans solved it with semicircular arches and volcanic ash concrete. Li Chun solved it with a flattened segmental arch and open spandrels in 605 AD. The Darbys solved it with cast iron. The Roeblings solved it with steel wire cables spun in place, and they overbuilt by a factor of 6 because they knew what they didn't know. Freycinet solved it by putting concrete into compression before the loads even arrived. Leonhardt solved it by running cables directly from towers to deck in a fan of elegant efficiency. And every single one of them was doing the same thing, finding a way to make the forces flow. That's what I find so beautiful about bridges, honestly. There's an underlying unity to all of it. A suspension bridge and a Roman arch look nothing alike. They're separated by 2,000 years and completely different materials and construction methods. But the physics is the same. The arch puts its material in compression. The cable puts its material in tension. Both are finding the most efficient path for the forces. Both are, in a sense, the same shape. A catenary curve, one flipped upside down. The arch is a frozen cable, inverted. The cable is a hanging arch. Robert Hooke figured that out in the 17th century, and it's still one of the most elegant insights in all of structural engineering. And the failures. We've talked about so many failures tonight. The Dee Bridge Angers, Tay Bridge, Tacoma Narrows, the box girder collapses, the I-35W in Minneapolis. Every one of them was a lesson written in the most painful possible language. Every one of them revealed something that engineers thought they understood but didn't. Not fully. The D Bridge taught us that cast iron couldn't handle the dynamic loads of railways. Tacoma Narrows taught us that wind isn't just a static push. It's a dynamic, living force that can set a structure dancing. The box girder crises of the early 70s taught us that thin steel plates under compression can buckle in ways that simplified calculations don't predict. And Minneapolis taught us that even a well-understood structure can harbor a hidden flaw for 40 years if nobody thinks to look for it with the right tools. There's a humility in that, I think. Good engineering has always required humility. The willingness to admit that your model of reality might be incomplete, that the next bridge might encounter something you haven't imagined. The best engineers in history have been the ones who built in margins for their own ignorance. Roebling's six-fold safety factor on the Brooklyn Bridge cables wasn't just conservatism, it was wisdom. It was an acknowledgement that the world is more complicated than any calculation can capture. And tonight, as you're lying there, maybe drifting in and out, I hope some of these stories have settled into a comfortable place in your mind. The next time you drive over a bridge, any bridge, even a small highway overpass, you might notice things you didn't notice before. The way the beams sit on their supports, the expansion joints that let the deck breathe with the seasons, the cables, if it's that kind of bridge, sweeping upward in their graceful curves, each one carrying its share of the load. You might think about the engineers who designed it, who ran the calculations, who lay awake at night wondering if they'd gotten it right. You might think about the concrete slowly curing, the steel tendons inside it pulled taut like guitar strings, holding everything together through forces you can't see, but that are always, always there. Bridges are one of the oldest things humans build, and one of the most fundamental. Before we had writing, before we had cities, we were probably laying logs across streams and stepping carefully to the other side. The impulse to cross, to connect, to refuse to let a gap in the landscape be the end of the journey. That's deeply human. And every bridge ever built, from a fallen tree across a creek to the soaring cables of the 1915 Chanakali, is an expression of that same impulse, refined by centuries of mathematics and material science and hard-won experience, but rooted in something much simpler. We see the other side, and we want to get there. So let that thought settle. Let the cables hold their weight. Let the arches carry their compression quietly down into the earth, the way they've been doing for 2,000 years. The forces are flowing, the structure is sound, and everything is holding together exactly the way it should. You don't need to think about any of it anymore. The bridge is there, it's doing its job, and you can rest